All right, good evening and welcome to lecture. Excuse me, we are still in chapter 7. According to the syllabus, we're finishing it up tonight. I don't think we'll quite get there, but on Thursday, we should finish up chapter 7 and start chapter 8. All right, so where we left things, last Thursday with a discussion of molarity, which is abbreviated with a capital M, and molarity is equal, it's a concentration unit equal to the moles of solute over the liters of solution. All right, so that is the definition of molarity. And molarity allows us to solve problems like the following. So, concentrated HCl, the most concentrated solution of hydrochloric acid you can buy, has a mass percent of 37% by mass. All right, so 37% HCl by mass is the most concentrated solution of hydrochloric acid money can buy. The density of this solution is 1.013 grams per milliliter. Determine this solution's molarity. All right, a problem unlike any problem we've ever seen before. So that makes this great practice for the exam. The first thing we want to find, the first thing we want to do when we solve a new type of problem, any type of problem, even an old one, is we need to identify what we're trying to find. And we are trying to find the molarity. Anytime you're trying to find a quantity with an equation, write that equation out. It is the moles, molarity is moles of HCl over liters of solution. All right? Now, once you know what you're trying to find, you should identify the pieces of information that you're given. All right? Now, what we're given in this, we're told that the density of our solution is 1.013 grams per 1 milliliter. All right, density is a ratio. And something that's important to note is this is the density of a solution. So this is 1.013 grams of solution over milliliters of solution. All right? Now, the other piece of information that we're given is we're given a mass percent of HCl, and that is 37 grams of HCl. Well, hang on. I technically didn't skip a step, but I want to draw this out a little bit. So we're told that this is 37%. All right. Now, if you're looking at these two things and you're like, I don't see a way forward, you're not alone. This can be one of the harder problems to visualize, which is why I want to take my time to do it. If you're feeling stuck and you're dealing with any percentage concentration, percent mass, percent volume, percent mass to volume, take a moment and think about what this 37% means. That 37% by mass means that you have 37 grams of HCl in 100 grams of solution. All right, that is what that 37% means. In 100 grams of solution, 37 of those grams are HCl. And once you compare this ratio to the ratio we're trying to find, you'll see that we actually just need to do 2 unit conversions. We need to convert grams of HCl into moles, right? You got to convert grams of HCl to moles. The second, and this one might prove a little harder, we'll see, we need to convert grams of solution into liters of solution. If we can do these 2 unit conversions, then we will have converted percent mass into molarity. All right, so let's take this one step at a time. We have 37 grams of hydrochloric acid in 100 grams of solution. All right. We need a unit conversion that is going to convert grams of HCl to moles of HCl. The only unit conversion that can do that is molecular mass. So we need to calculate molecular mass for HCl. Chlorine has an atomic mass of 35.45 AMU. Hydrogen has an atomic mass of 1.008 AMU. So we add, doesn't leave a lot of room. When we add these together, we get 36.458 AMU. The last sig fig of the numbers that I was using needs to be in the second decimal place. So that is the last significant digit. This molecular mass has 4 sig figs. So this is 36.458, but this number has 1, 2, 3, 4 sig figs in 1 mole. Notice that grams of HCl cancel grams of HCl, and now we have moles in the numerator, which is awesome. That's what we're after. Now we have to go to work on our denominator. Now, if you're wondering, okay, where do we go from here? Take a moment to recall when we were laying out our information at the very beginning. The density of a solution gives you the ratio to go between grams of solution and a volume of that solution. Now, we want to get to liters eventually, and this is in milliliters, but we can do that later. But right now we want to use the density of our solution to convert our denominator from grams from a mass unit to a volume unit. So first, we want grams of solution to cancel. we want to be left with milliliters of solution. And our density tells us that 1 milliliter of solution has a mass of 1.013 grams. All right. Now look, grams of solution, cancel grams of solution. Now we're left with milliliters, which granted is not molarity. Molarity isn't moles per milliliter, it's moles per liter. So we have one last unit conversion to perform, and that is we need to convert from milliliters to liters. And 1 milliliter is 10 to the negative third liters. And now we've got moles per liter. That is units of molarity. So now we can crunch our numbers. So we have at the beginning 37 divided by 100 times 1 divided by 36.458 times 1.013 divided by 10 to the negative third. So I'm getting a value of 10.280596.9. All right, that's my value. Sig figs wise, I'm limited to 2 significant digits because my mass percent only has 2. So that's going to limit us to 2. You count off your first 2, 1, 2. This 2 rounds down. But I have a problem. I can't write 10 because 10 only has 1 sig fig and I need to have 2. So I'm going to need to write this in scientific notation. 1.0 times 10 molar. That's how you say a solution whose units are molarity. Molar. 1.0 times 10 molar HCl. And this is my final answer. So this is one type of problem. Again, we did a problem similar to this of last week, converting from percent mass to percent mass to volume. And this was similar, where we were just manipulating our initial concentration unit to change the units to find its concentration in a different unit. In this case, percent mass converted to molarity. All right. But there are other types of examples we can do that involve molarity. Examples like the following. Oops. Sorry, I want that to be in black. Aqueous. Sodium hydroxide. Reacts with aqueous hydrochloric acid. Nope, not hydrochloric acid. Sulfuric acid. To produce water and aqueous sodium sulfate. Part A. Write a balanced chemical equation for this reaction. Part B. Determine the theoretical yield of water if 50 milliliters of 1.0 molar sodium hydroxide is mixed with 35.00 milliliters of 1.0 molar sulfuric acid. All right. Step number one is we need to balance this chemical equation, and to do so, first we have to write out what our reactants and products are. So first off, we're dealing with sodium hydroxide. Now, sodium has a charge of +1 when you look at the periodic table. Hydroxide is a polyatomic ion, which if you don't have it memorized, it should be on your equation sheets. And so these two will combine in a 1-to-1 ratio. There's aqueous sodium hydroxide. We're told it reacts with aqueous sulfuric acid. All right, sulfuric acid. Well, this is an ic acid. That means that it's based on an ion that ends in 8. Sulfate has a charge SO4 a formula SO4 with a -2, kind of polyatomic ion that should be on your equation sheet if you don't have it memorized. And the reason why the charge is important is the charge tells you how many hydrogens you give this ion to make it an acid. So charge of -2 means that sulfuric acid will need two H's out in front of it. Now our products are water, H2O, which is a liquid. That wasn't explicitly stated, but we're in an aqueous medium. You can't have aqueous water. It's just pure liquid. And then sodium sulfate. Now here we have to pair our positive sodium ion with our negative sulfate ion. And because we're +1, we're going to need 2 sodiums to balance with sulfate's charge of -2. So this will be plus Na2SO4, also in the aqueous phase. All right. Now, this may not necessarily be balanced, but this is our chemical equation with reactants and products written out. So we need to see if it's balanced, and if it's not, we need to make it so. All right, so first things first, we need to take an inventory of all the atoms on both sides of this reaction. We have sodium, oxygen, hydrogen, and sulfur. Sodium, oxygen, hydrogen, and sulfur. On the reactant side, there's 1 sodium. We have 1 oxygen coming from sodium hydroxide and 4 more coming from sulfuric acid. We have 1 hydrogen coming from sodium hydroxide and 2 more coming from sulfuric acid, and then we have 1 sulfur atom. That's the reactant side. The product side, we have 2 sodium atoms, one oxygen atom coming from water, 4 oxygen atoms coming from sodium sulfate, 2 hydrogens coming from water, and 1 sulfur coming from sodium sulfate. So when I look at what's wrong, I see that hydrogen's not balanced, and neither is sodium. Of the 2 of these, sodium looks easier to fix, so I'm going to start there. If we multiply sodium hydroxide by 2, this will change our sodium, oxygen, and hydrogen counts. Sodium now we have 2 on the reactant side. Oxygen, we have 2 coming from sodium hydroxide, 2 oxygens. We still have those lingering 4 from sulfuric acid. And then for hydrogen, we have 2 coming from sodium hydroxide, plus the other 2 from sulfuric acid. Now, oxygen's out of whack, which is disconcerting, but hydrogen seems relatively fixable. We've got a total of 4 hydrogen on the reactant side, only 2 on the product side. So let's multiply water by 2. This is going to balance our hydrogen. It also will change and turns out balance our oxygen as well. Because now we have 2 oxygens coming from water. So we have 2 plus 4, and we're all good. All right, so this is our balanced chemical equation. Let's clear this board up a bit. All right, now we were asked to determine a theoretical yield of water, and we were told that we had a 1.0 molar solution of sodium hydroxide. We had 50.00 milliliters of it. And we were told that this was mixed with a 1.0 molar solution of sulfuric acid, and that we used 35 milliliters. And we're asked to find the theoretical yield in grams of water produced by this reaction. Okay. Unlike anything we've ever seen before, which you already know is good practice, this is something that you'll see over and over and over again. Something that you want to get very familiar with is this classic pairing of concentration and volume, molarity and a volume. The reason why you see this over and over and over again in stoichiometry type problems is molarity is equal to moles over liters. So if you're given the molarity and a volume, what does that allow you to solve for? Moles. It lets you solve for moles, and then it lets you do stoichiometry problems. Excuse me. So you're going to see this over and over. This requires a little bit of algebra, right? Molarity is equal to moles over liters. So if you multiply both sides by the denominator, you'll see that this equation rearranges so that moles of solute are equal to the molarity of the solution times that solution's volume in liters. So we're going to be using this to solve. One thing you may notice is our volume here has to be in liters, and these volumes that we are given are in milliliters. So we've got to do a unit conversion for each one. But once we have that, we just multiply these together, and that will allow us to find moles of solute. Another thing you'll notice is that we're given starting quantities of both sodium hydroxide and sulfuric acid. Right, that's because this is a limiting reagent problem, so we will need to calculate the amount that we could make from sodium hydroxide, then the amount that we could make from sulfuric acid, and then pick whichever one is smaller. That will be our theoretical yield. But first, let's do our unit conversions. 50.00 milliliters. We want to convert to milliliters. Sorry, we want to convert to liters. 1 milliliter is 10 to the -3rd liters when I punch this into my calculator. My calculator tells me the answer is 0.05. However, 50 milliliters has 4 sig figs, and this 0.05 only has 1. So we need to add 3 zeros. So 50.00 milliliters is 0.05000 liters. When we perform the same unit conversion for 35 milliliters, we'll see that a very nearly identical answer solution, near identical answer arises. So you punch this into your calculator. Your calculator will tell you it's 0.0. But again, we need 4 sig figs. So we got to add a couple zeros. Now that we know what our volumes are in liters, we can begin our calculation just like any other limiting reagent calculation. So we have, starting with sodium hydroxide, 1.0. Pro tip, whenever you're given molarity as a unit and you need to do stoichiometry, it's better to just write this as a numerator and denominator. I find when I write that capital M, that it's easy for me to forget that there's even a denominator there. So it just becomes clearer if instead of writing a capital M, you write this as moles of sodium hydroxide over liters. We're going to multiply this by our volume in liters, 0.05000 liters. All right, so that liters cancel out. Next, we're going to multiply we need to convert from moles of sodium hydroxide to moles of H2O. This unit conversion we get from our balanced chemical equation. It is a 2-to-2 or 1-to-1 mole ratio. Moles of sodium hydroxide cancel. Finally, we need to convert from moles of water to grams of water. And water has an atomic, well, oxygen has an atomic mass of 16, hydrogen 1.008, but we got 2 of them. So this will come out to be 18.016 AMU. Using the numbers that I'm using, our last sig fig would be the second decimal place. So this number has 4 sig figs. So this would be 18.016. 1, 2, 3, 4 sig figs. And 1 mole. Now, moles of water cancel. We're left with grams. All right, so let's crunch our numbers. 1 times 0.05 times 2 divided by 2 times 18.016. My calculator is giving me a value of 0.9008. This would be grams of water. Sig figs wise, be limited to 2 because our starting molarity only has 2 sig figs, but I'm going to wait because I don't even know if this is my answer. Right? I don't know if this is my answer because this is a limiting reactant problem. And I need to do the calculation with my starting quantity of sulfuric acid if I'm going to know, or if I'm going to determine which one is limiting and therefore what my theoretical yield is. So starting with 1.0, and again, I'm dealing with molarity here. So I'm going to explicitly write out moles of sulfuric acid per, so that's a 4, or shoot, now that's less clear. There we go. Moles per liter. I'm now going to multiply by 0.03500 liters. So liters cancel. Next, I want to cancel moles of sulfuric acid to moles of water. And this ratio comes from the balanced chemical equation. It is a 1 to 2 molar ratio. So moles of sulfuric acid cancels. Next, cool thing is we've already calculated our molecular mass of water, so we don't have to do that a second time. 18.016 grams per mole. And there's only 4 sig figs in this numerator. Moles of water cancel. Now let's crunch our numbers. 1 times 0.035 times 2 times 18.016 gives me a value of 1.26112. Sorry, that's not moles of water, that's grams of water. Again, I would be limited to 2 sig figs here because of my starting molarity, but now what I need to do is compare these two, and because this is the smaller of my two values, this is my theoretical yield. Because whenever you're given 2 initial quantities, you do theoretical calculations on each one, and then whichever is smaller, that is the one that you select for as your answer, as your theoretical yield. So then just for the sake of completeness, we'd have 2 sig figs. So our answer would be 0.90 grams of water for our theoretical yield. All right. Before we leave this topic of molarity, there's one last problem type that we need to discuss. One more concept that we need to discuss, and that is the topic of dilutions. Sadly, there is no shortcut. Sadly, there's no shortcut other than, I guess, getting fast at this calculation. Yeah, that's just practice until it becomes like breathing. This next type of problem is not nowhere near as strenuous, and it is the topic of dilution. All right, now the process of dilution it's a simple concept. You simply add pure water, or I should say add solvent, because the solvent doesn't have to be water, to decrease the concentration. All right, so if you take, for example, molarity, which equals moles of solute over liters, adding water increases the denominator and what happens when your denominator gets bigger? Your value gets smaller. Right, so your concentration decreases because your denominator, the denominator of your expression, is increasing. All right, and that's what we're doing with dilution. Now, if you're wondering why would we do this, isn't a higher concentration better? Depends upon the context. Humans have been doing this for years with liquor, for example. If you take a shot of your poison of choice, it's gonna kick like a mule, right? If you throw back a shot of bourbon, punches you right in the face. If you take that same shot and pour it into a ginger ale, and you drink the whole ginger ale, you've consumed the same amount of alcohol, but the concentration has been lower, so it doesn't come at you all at once, right? Another reason why dilution is useful on the more chemical side of things, I realize none of us have stepped foot in a lab for over a year, but if we did, turns out that chemical companies will rarely sell the acids that you need in the proper concentration that you need them at, in the concentration you need them at for each experiment. So if an experiment calls for 0.1 molar HCl or 0.15 molar HCl, you're not buying different bottles of HCl to do all those experiments. What you're doing is buying one bottle of super concentrated HCl. And then you dilute it, you take some of that and add enough water so that the concentration will be appropriate for your experiment. All right, people who work in stockrooms for chemical labs do this all the time, diluting solutions from concentrated down to the appropriate level that's needed for a particular experiment. So dilution's super practical, super hands-on, and there's an equation for it. The dilution equation is M1 V1 is equal to M2 V2. All right, and this is M1 is, well, here. let's do this in a more. M1 is initial concentration. V1 is initial volume. And as you can imagine, M2 is also a concentration, V2 is also a volume, but both of these are final. So final concentration, final volume. All right. So here's how you use, and by initial and final, initial is before adding water, final is after adding water, after you've done the dilution. These can be for any concentration unit, any volume unit, as long as they're both the same. All right. So you can solve problems like the following. Actually, I do this in two parts. So, you need 100.00 milliliters of 3.00 molar HCl. Determine the milliliters of 10.28 molar HCl you would need to use, or you would need, and the milliliters, sorry, hang on. Let me save that for the very end. All right, and it sounds, sorry, like my neighbor's mowing the lawn, and my window's right open, so hang on one second, I'm gonna close the window. All right, still, we can still hear it a little bit, but what you're gonna do? You'll lecture through it is what you're gonna do. So, so let's see, where were we? Determine the milliliters of 10.28 molar HCl. Sorry. Let's just start all over. And the milliliters of pure water. You need to make this solution. All right. So we need to find two things actually in this problem. Let's write them down. we need to find the volume of HCl and we need to find the milliliters of pure water. All right, we're going to focus on finding V1 first because it's right here. And you'll notice that we're given final volume and final concentration, both here and here. In addition, we're given initial concentration right here. So we have all the pieces. Excuse me. Was able to mute the mic just in time. We have all the pieces to find our initial volume of HCl. Once we have that in hand, we'll come back to water, but let's go ahead and move on this. So first off, M1V1 equals M2V2. We want to find that initial concentration, so we divide both sides by M1. M1 cancels. And we get a new expression, initial volume is equal to M2 V2 over M1. Our final molarity is 3.00 molar. Our final volume is 100.00 milliliters. And our initial molarity is 10.28 molar. And you'll notice that molarity cancels molarity, and we're trying to find milliliters, so that is totally fine. So 3 times 100 is 300 divided by 10.28. This gives us a value of 29.1828,794. Sig figs wise, we can keep a maximum of 3 because our initial molarity has the most. This 8 is going to round up. So our volume of acid is 29.2 milliliters. That is our V1. So we have V1. Now what about milliliters of pure water? To answer this, we have to think about what is actually going on in the dilution process. All right? So for this dilution to go down, we are taking 29.2 mils of HCl and adding unknown amounts of pure water until it has a total volume of 100 milliliters, 100.00 milliliters. So how do you find the milliliters of water? Well, subtract 29.2 milliliters from both sides of this equation. 100 minus 29.2 comes out to be, let's see, we gotta round to the first decimal place here. 70.8 milliliters. This is the water added. Because we know the water added and that initial volume of HCl have to add together to our total volume of 100 milliliters. All right. So that is dilution. It's a pretty straightforward equation. It's not the worst type of problem in the world. It tends to be one that most classes do very well on in a testing scenario. Okay. So all right, so that is dilution. We're still going to be discussing solutions, but we're going to kind of move on to a new topic, one that's called colligative properties. Colligative properties. All right. So, colligative properties, simply put, these are properties of a solution though I can't I can definitely say that they won't exclusively be dilution problems. There will definitely be dilution problems on the next exam. So it'll be a meet you in the middle kind of gift, but it won't be 100%. That's for sure. So colligative properties are properties of a solution that change depending on the amount of solute present the amount of solute in that solution. All right, so colligative properties are simply properties that change. All right, so for example, adding solutes will, for example, lower vapor pressure. All right, adding solutes will lower vapor pressure. Adding solutes will increase boiling points. That's why, for example, when you're like cooking pasta, for example, you put it in the boiling water. Often a recipe will tell you to add salt to the water. It's actually not to season the pasta. It's because adding salt to the water, adding a solute, will increase the boiling point, which means that that solution will boil at a higher temperature than water boils. And if you're boiling at a higher temperature, that means your pasta will cook faster. So it's actually to increase the speed, the amount of time it takes for that pasta to cook, not actually for flavor. Another a colligative property would be freezing point. Adding a solute will decrease the freezing point. This is why, for example, if you've ever lived or driven somewhere that it snows, states in the Midwest will put salt on the roads. And no, it's not to corrode your cars, although that can happen as well. It's to lower the freezing point of water below 0 degrees. If there's salt on the road, then the slush will stay slush instead of turning to ice, which will make your car lose traction, slip, and cause all sorts of accidents. We are going to park on the colligative property of freezing point depression, or freezing point. I'm going to park on this for a minute and kind of dig a little deeper into freezing point depression. So let's talk about freezing point depression. All right. That the amount by which a solution's freezing point will decrease, it depends upon the concentration of a solution, and this deviation from the normal freezing point is mathematically quantifiable with the following equation. And it's the change in freezing point, that's what the delta TFP is equal to -1 times I times molal times Kf. This is the equation for the change in freezing point. So this right here, this is just the change This is the change in freezing point. And it actually, there's another equation for it. It actually equals, the change in freezing point is equal to the freezing point of the solution minus the freezing point of the pure solvent. All right, so that's another formulation for the freezing point, or change in freezing point. Actually, I'm going to simplify this real quick. Oops. All right, so that is the change in freezing points. Also can be written like this. You'll see we'll need both of them in just a minute. KF, we'll go for the low-hanging fruit. KF, this right here, is the freezing point constant. Something to know about the freezing point constant is it's actually unique to every solvent. So the freezing point constant of water will be different than the freezing point constant of ethanol, which will be different than the freezing point constant of benzene, for example. So for each individual solvent, you need to look up what that specific freezing point constant is. And it has units, really weird units, of kilogram degrees Celsius over moles. Right, those are the units for the freezing point constant, freezing point depression constant. So those are two of our four variables. Let's take a look at the other two. So this is something called the Vant-Hoff factor. All right, and the Vant-Hoff factor is the number of particles a solute breaks into when dissolved. All right. You might be going, Josh, you just told me the definition. I still have no idea what that means. And the Vant-Hoff factor is easier to illustrate with pictures than for me to tell you with words. So, for example, let's look at aqueous sodium chloride. All right, the number of particles in solution, aqueous solutions, aqueous ions separate into their cation and anion, separate from their cation and anion pairs. So sodium is just free-floating sodium. Chloride is free-floating chloride. And you can see that sodium chloride breaks into one sodium ion and one chloride ion. So the Vant-Hoff factor for sodium chloride is 2. There's 2 ions there. Magnesium chloride will break into magnesium cations plus 2 chloride anions. Right, so we have 1 magnesium ion, 2 chloride ions, so the Vant-Hoff factor here for magnesium chloride would be 3 because it's breaking apart into 3 particles. Something worth noting. Is that's for ionic compounds, covalent compounds, for example, ethanol does not break down. Only ionic compounds, aqueous ionic compounds do. So aqueous ethanol doesn't break into any particles. It's just aqueous ethanol. And so because there's only 1 particle in solution, aqueous ethanol has a Vant-Hoff factor of 1. Okay, so however many particles your thing breaks into, that's your Vant-Hoff factor. Your aqueous ionic compounds break into all their anions and cations. Covalent compounds don't break at all. So that is the Vant-Hoff factor, leaving only this mysterious quantity, which I have written out as molal. This one's a weird one. So in the book, what I have written here as molal, the book just writes as M. Technically, it's not just M. It's M in italics. All right. I don't know about you, but my italics M just looks like my normal M. And so I didn't want to write this as an M because if I did, you'd look at that and think mass, and it's not mass. Italics lowercase m is the abbreviation for a concentration unit known as molality, not to be confused with molarity. This is molality. All right. Molality, which I will always just write this as molal to be clear. All right. But in the book, when you see the italics M, it's molality. The italics lowercase m, it's molality. So you just got to know and sort that out for yourselves. But I will, in lecture here, always write it as molal. Molality is equal to moles of solute divided by kilograms of solution. Moles of solute divided by kilograms of solution. All right. So now that we have discussed every component of this equation, this is the equation that tells us how much a freezing point will change as the concentration of solute increases, as the concentration of solute changes. Let's go ahead and do an example. All right. Determine the freezing point of a pure solvent if a 2.12 molal solution of KBr freezes at 15.6 degrees Celsius, period. Note the freezing point depression constant for the solvent is 1.73 kilograms degrees Celsius per mole, and assume the Vant Hoff factor for KBr is the same as aqueous KBr. All right. So let's do this. First, what are we trying to find? We're trying to find the freezing point of the pure solvent. All right. The only equation we've seen, well, so first off, actually, let's look at what we're given. All right. Because we're dealing with freezing point depression, right? We've got a freezing point depression constant, you should immediately write down change in freezing point is equal to -1 times the Vant Hoff factor times the molality times the freezing point depression constant. There's another equation with freezing point depression, and that is the change in freezing point is equal to the freezing point of the solution minus the freezing point of the pure solvent. And that is what we're trying to find. So if we can find the change in freezing point and the freezing point of the solution, we use this second equation to solve it. Now let's look at what we're given. We're told what the molality of the solution is. Molality is 2.12. Now the units will always be moles over kilograms. So we know molality. We're also given Kf, 1.73 kilograms degrees Celsius per mole. So we know Kf. We're also given, actually, the Vant Hoff factor. We're told to assume the Vant Hoff factor is the same as KBr. Well, KBr has 1 potassium and 1 bromide, so the Vant Hoff factor is 2. So because we know our Vant Hoff factor, our molality, and our Kf, we can solve for the freezing point depression, which means we know how to solve for this, and we can find the freezing point of our pure solvent. So that is the strategy. That is the battle plan of sorts. Now let's dig in, use some algebra to actually solve this problem. So first off, let's find our change in freezing point using this equation, Vant Hoff factor times molality times Kf. So the Vant Hoff factor is 2, our molality is 2.12, and this is moles per kilogram, and then Kf is 1.73 kilograms degrees Celsius over moles. You'll notice that moles cancel, kilograms cancel. We're just left with degrees C. So let's see, we got -2 times 2.12 times 1.73 gives us a value of -7.3352 degrees Celsius. Sig figs wise, we're limited to 3 sig figs by both our Kf and our molality. So 1, 2, 3. 5 is going to round up. So our change in freezing point is -0.34 degrees Celsius. Don't be freaked out by the negative sign. That just means the freezing point dropped, which is what will happen because we're dealing with freezing point depression. All right, now that we know our change in freezing point, we can use this to solve for the change, to solve for the freezing point of the pure solvent, because the change in freezing point is equal to the freezing point of the solution minus the freezing point of the solvent. first thing we got to do is we need to isolate the freezing point of the solvent on one side of our equation. So we need to subtract the freezing point of solution from both sides. So our change in freezing point minus the freezing point of our solution is equal to -1 times the freezing point of our solvent. And we don't want to know what -1 times the freezing point of our solvent is. We want to know what the actual freezing point of our solvent is. So we're going to multiply both sides of this equation by -1, so it becomes positive. Finally, this gives us that the freezing point for our solvent is equal to -1 times the change in our freezing point plus the freezing point of our solution. So now we can plug in our numbers. -1 times our change in freezing point for the solution is -7.34 degrees Celsius. And the freezing point of our solution was right there. It's 15.6 degrees Celsius. And happily, negative times a negative makes a positive. So I take 7.34 plus 15.6. And I get as a value 22.94, but we have to ask ourselves, what about sig figs? Our change in the freezing point of our solution has its last significant digit in the second decimal place, but our freezing point for our solution has its last significant digit in the first decimal place, so we will have to round to that first decimal place. 4 rounds down, and we find that the freezing point of our pure solvent is equal to 22.9 degrees Celsius. All right. We're almost done with chapter 7. We just have a little more to talk about osmosis, osmotic pressure, etc. But I'm going to wait to begin that discussion for Thursday. So we'll beginning a lecture on Thursday, wrap up chapter 7, and then dive into chapter 8. So that's it for lecture. I will see you guys in about 15. Tonight for lab, it's just open office hours. So hit me up with any questions whatsoever. Later, dudes.